This is lecture 20 of Physics 210A, Thermal Physics. And in the past few lectures I have discussed phase transitions, and we are therefore in a position to discuss third law of thermodynamics as well as open systems, and that's going to be the content of the next two lectures. So today's lecture is going to be on the third law of thermodynamics. And it's based completely on chapter 12 of Finn's thermal physics. So to motivate, let us go to the entropy calculation, where we had written that delta S is equal to integral dq over T over a reversible process. And if we integrate from T equals 0, so suppose the integral is performed from T equals 0, then I have S equals integral 0 to T dq T reversible plus some S0, which can be written as integral 0 to T Cp dt prime over T prime plus S0, where S0 is the entropy at T equals 0. And it is this S naught that the third law talks about. So, third law of thermodynamics is concerned with S0, that is the value of entropy at T equals 0. Although T equals 0 cannot be attained, so we can say this is concerned with asymptotic value of S as T tends to 0. So this build up to third law starts with Nernst's theorem. So this is from 1906 onwards, and it starts with Nernst's heat theorem. This theorem is based on the observation is that in a chemical reaction which occurs at the same end temperatures, so this is concerned with chemical reaction with the same temperatures at the beginning and at the end of a chemical reaction. What Nernst observed is that delta G, which is negative if you are going towards an equilibrium state, it becomes smaller and smaller. And delta H, the change in the enthalpy, also becomes smaller and smaller in magnitude. So, he anticipated that the change will vanish as T tends to 0. This is temperature. So, delta G, which is delta H minus T delta S, let me write T same at the end points. This implies that delta S is also changing, and Nernst postulated that delta S tends to 0 as T tends to 0. So, these two curves meet each other. So, the theorem is entropy change in a process that occurs between a pair of equilibrium states. So, for example, if there is a chemical reaction taking place, you have two equilibrium state, one the end products and one the chemicals reacting. So, it is occurring between a pair of equilibrium states. And how does this happen? This happens because of the change in external parameters tends to 0 as T tends to 0. So, what does it mean? Let us try to understand this, and that will lead to the statement of Planck for the third law. So, suppose I have a crystal. Made of elements. So, there is some sort of a crystal, let us make that one element, and another element. These are both in equilibrium. So, let us call them element 1 and the other one element 2. And now, suppose they form a compound, and I have a third crystal which is made of these two elements. So, what I have is right here is the crystal which is made of these molecules that are formed by these two elements. So, suppose the entropy of this system was some S0, this was some another S0, let's say 2S01. The entropy of the final system here will also be such that there will be no change delta S between entropies of crystal of element 1, crystal of element 2, and that of the compound. Made of element 1 and element 2. Of course, we are conserving the number, and moles are the same and all that. So, this led Planck to give the statement for the third law, and that is this. And the statement is that entropy of all perfect crystals is the same at absolute 0. That means all perfect crystals at absolute 0 will have the same entropy, and therefore, it may be taken to be 0. Since this is the same, I can take the reference point and make it 0. Now, I just want to make a note here, and the note is, although Planck's statement is for perfect crystals, it is now believed that it is true for all materials, including liquids and other disordered materials. So, just as an example, because you may ask, which material remains liquid as you take temperatures to a 0. For a material that remains liquid at very low temperatures is liquid helium. So, even for that, one would say that the entropy goes to 0 or becomes very small as temperature is taken to very, very low values. Now, can we check this? The question is, can we test Planck's statement? And the answer is yes. And this is done by looking at entropy change of different forms known as allotropes of same material. Examples: one, if you look at pure tin, it exists in two forms and more, but right now we'll consider these two forms, which are known as gray and white tin. Also known as alpha and beta tin. Above 286 K, the stable form is beta tin. Which is crystalline and metallic. On the other hand, below 286 K, the stable form is alpha tin, which is powdery. Let me ask you a question here. How are the Gibbs energy per mole for alpha and beta tin related at T above and below 286 K? Second example is that of sulfur. It also has many different forms. So, at atmospheric pressure, the common forms are monoclinic, that is the kind of crystal one is talking about, and other one is rhombohedral. This is another kind of crystal one is talking about. The monoclinic is known as beta sulfur, and the rhombohedral one is known as alpha sulfur. So it has two forms, beta sulfur and alpha sulfur, and they also at atmospheric pressure depend on which form is seen, depends on the temperature. So above 386 K beta sulfur is stable, and below 386 K is the alpha sulfur, that is stable. So what you see if you just plot the entropy, here is temperature 386 K, so suppose I were to plot the entropy of these two forms, then I have the entropy of the two forms like this, and there is a jump in the entropy at 386 Kelvin, and you can suppose they start from the same point, some point where the entropy is S0, then I can calculate the entropy change and find out if S naught is common or not. So on the left is alpha sulfur, and on the right is, this one is beta sulfur. And there is a phase transition at 386 K. This is the first order phase transition, and therefore there is a latent heat involved. Let me call the lower point point A, and this is point B, and we are plotting this entropy with respect to temperature this way. This is T equals 0. Let me, before I proceed further, ask you a question. What tells you that the transition from alpha sulfur to beta sulfur at 386 K is first order? Now I can calculate the entropy at B by two different ways. One is by integrating from 0 to 3 we're writing this wrong. Let me just correct this. This is 368K. This is 368K. So this will be up to 368K Cp dt prime over T prime, where Cp is for the beta form. Now, experimentally, you may ask, how do you get beta form below B? So, experimentally, one can have beta sulfur below 368K in what is known as metastable state. So, you have to be doing these experiments very carefully. You disturb the metastable state, it immediately goes to the more stable state of alpha sulfur. So, one does it very carefully. So, this is one way one can calculate SB, and we will call it SB minus S0. The other way one can calculate SB minus S0, SB minus S0, this will be equal to SB minus SA plus SA minus S0. So, what is one doing? I am looking at this graph. Starting from S0, I have this alpha sulfur, this is beta sulfur, and this is at 368 K. On the right is going temperature. This is A and B. Now, SB minus SA is nothing but the latent heat divided by 368 temperature, and SA minus S0 is given by 0 to 368 K Cp of alpha form dt prime over T prime. Now, again, Cp alpha and Cp beta can be measured. Cp alpha is easier to do because this is already a stable form, and one can calculate these numbers. So, the first method, which is 0 to 368 K Cp beta dt prime over T prime, gives close to 37.82 plus minus 0.40. So, this is joules per Kelvin, not close to, just the number measured experimentally. And the second method gives 0 to 368 K Cp alpha dt prime over T prime plus L over 368. This gives 37.95 plus minus 20 joules per Kelvin. These numbers are the same within the experimental error, 0.20. So, these numbers are equal within experimental error, and this implies immediately that S naught is the same for both the materials. And that shows experimentally that Planck's statement is correct. The entropy for perfect crystals, and then as noted earlier, for other materials goes to 0 or goes to a constant as t tends to 0, and we can take this to be 0. Now, third law has certain consequences, and one consequence you may have already noticed when I was doing this calculation is that when I do the integral dt prime over t prime from 0 to some temperature, I get a log term, and yet this integral is finite. That means Cp must be going to 0 as t tends to 0. So, this is the kind of consequences we are now going to talk about, and these are consequences of the third law. One consequence you may have already anticipated is Cp t tending to 0 going to 0. Why? Otherwise, integrals done in the previous slide would not have been finite. Nonetheless, let's show that. So, if I have Cv, which is equal to T partial S over partial T V, this will go to 0 because delta S goes to 0 as T tends to 0 by the heat theorem. So, Cv goes to 0. Similarly, Cp, which is T ds dt at constant pressure, will also go to 0 as T goes to 0, since delta S goes to 0 as T tends to 0 by Nernst theorem or the heat theorem. So, this is one consequence of the third law, that all the heat capacities will go to 0 as temperature tends to 0. Similarly, you can talk about other derivatives. So, next we are going to talk about thermal expansion coefficient, which is beta equals 1 over V dV dt at constant pressure. Now, if I can relate this to entropy change, then I can show that beta is 0, and that relationship is given by Maxwell's relation. This is minus 1 over V. dV dt at constant P is ds dP at constant temperature. And as T goes to 0, delta S goes to 0, and this implies ds dP at constant T goes to 0 as T goes to 0. As a result, beta tends to 0 for T tending to 0. So, thermal expansion coefficient also vanishes as T tends to 0. Next, check if Curie's law, which is, we have been talking, the susceptibility, magnetic susceptibility being equal to C over T. is valid for temperatures tending to 0. Now, in this case, we will have to apply the first law or all laws involving the magnetization. So, in this case, we have du equals T ds plus B0 dm. We are talking about dilute and weak paramagnetic substance. Therefore, I have written the applied field B0. And from this, just to recall, I have du ds at constant m equals T and du dm at constant s equals B0. Now, what I want to do is check this, somehow bring in chi m and also entropy, because third law is finally related to entropy. So, let us check how we do that. Now, in this case, the derivatives you will have will be dt by dm at constant s equals dB0 by ds at constant m. So, this is no good for checking the Curie's law. Because there is an S down there. Similarly, you can check for other systems, and finally, what you are going to get is that it is the Maxwell relation obtained from G, the Gibbs free energy, that is appropriate for our purposes. You see, Gibbs and Helmholtz free energy talk about derivatives at constant V, constant T and constant P, which are very easy to do. So, let us look at the Maxwell relationship obtained from the Gibbs free energy, which is partial S partial B0 at T is equal to partial M partial T at B0. Before I proceed further, let me give you this exercise. Obtain this Maxwell relation. Now, you see, as t tends to 0, the left hand side of the equation above also goes to 0. And let us calculate dm dt. The magnetic moment of the sample is going to be the volume times the m, which is going to be V chi m B0 upon mu 0, which is V B0 upon mu 0 C over T. C over T is the chi m. And therefore, dm dt at B0 is equal to minus V B0 over mu 0 C over T square, and it goes to infinity as T goes to 0. So, left hand side and right hand side do not match, and this implies, because of the third law, which gives you left hand side being 0, Curie's law cannot be correct as t tends to 0. And there is a physical reason for it. The physical reason is that Curie's law is derived by assuming that all dipoles are independent. But as t goes to 0, magnetic dipoles interaction with each other aligns them. So they are no longer aligned only by external field, but due to this interaction with each other also. Now, next, I'm going to consider the first order phase transitions and see what dp dt is as t tends to 0. So dp dt is equal to delta S over delta V by Clausius-Clapeyron equation, and delta S goes to 0 as t goes to 0. So this means dp dt goes to 0 as t tends to 0 for all phase diagrams. So you can check all the phase diagrams have this slope going to 0 as t tends to 0. And finally, I'm not giving the proof of it, but just telling you that third law also leads to arguments that say no reversible adiabatic process starting at non-zero temperatures can possibly bring the system to 0 temperature. Many words here, so I'll give you a question. Think about how reversible adiabatic process cool the system, cool a system, and learn about cooling by adiabatic demagnetization, which is similar to in the first part I have said how adiabatic process can cool a system. For example, there is an adiabatic expansion of a system that will cool. Similarly, adiabatic demagnetization leads to cooling, so learn about that, and then we can discuss this in our discussion hour. With this, I'll conclude my lecture. The third law of thermodynamics has been discussed. Experimental verification has been demonstrated by presenting one experiment, and finally some consequences of the third law. Have been presented. Thank you.